So this question is about signal flow graphs and basically of control systems. So here's the questions. First of all, it's asking us to discuss the main advantages and disadvantages of feedback control over feed-forward control. Sketch a signal flow diagram of feedback and feed-forward systems. We're given, in fact, we should know what the state space equations are for a state space model. X dot equals x plus bu, y equals cx plus du, and it's asking us now to derive the updated version of these when we employ full state feedback using a feedback gain of k. Then it's basically asking us to draw the signal flow diagram for full state feedback control. So let's start off by thinking about advantages of feed forward control over any other method, as opposed to basically as opposed to closed loop. And obviously a feed forward system can be very simple because all we're doing is we're just we're calculating the input to a system and giving it the input, and that's it, we're finished. So it could be less expensive in this day and age. We're not, the computation's not a problem. It might be that the sensor's a problem, so we haven't got a sensor looking at what it's doing. We've certainly got no stability problems because we're not using feedback. So we're not using feedback, so we can't feed something back which will lead to positive feedback and therefore stability problems. And we can apply open loop when we know the relationship very well between the input and the output of the system. So actually a good example of an open loop system would be a stepper motor. We give it a pulse, it moves by a little tiny bit. And provided that we're using it within the realms of design specification, it'll be fine, right? We give it a pulse, we know it's going to move through, 0.2 degrees or something per pulse, or whatever it is. This is fine as long as there are no external disturbances. So, imagine you did have a stepper motor, right? And you're giving it its pulses, and it's going, it's moving a little step each time. Now imagine you actually held it or something with a spanner or something, so it missed a few pulses. Well, after that, the calibration's gone. You can no longer rely on what the input is relative to the output. So that is an example of a feed-forward system, but it can't deal with the fact that you could be disturbing it. So that's a big problem if you've got disturbances. And the disturbance could also be internal. It could be that there's something happening inside the mechanism as well as something happening outside. Another reason for using open loop is if it's difficult or expensive to actually measure what's happening. In fact, that's another reason people use stepper motors, because if you've got a stepper motor, you don't need to measure the position, because you can, first of all, you can almost be certain, if you're not overloading it, that you know where the position is relative to when it started. So it basically makes it economically feasible to have something cheaper. Although, of course, we could measure it with an encoder if you wanted to as well. So, one problem with open loop is you do need to know the relationship between the input and the output of the thing you're controlling. And if this changes over time, you may well need to recalibrate your system, your inverse model. In fact, we'll come to that in a sec, in order to deal with that. And like we said, it is sensitive to disturbances, and it can't, if it was a stepper motor, it could never recover, for example. So what about feedback control, closed loop control? Well, this is actually comparing what we actually get from the output with what we wanted and generate an error. And the big advantage of this is, first of all, we can reduce the effect of disturbances. So, if you had a system and it was rotating round to the angle that you've asked it for, and then you tried very hard to stop this thing moving, it would keep trying to get there because it's measuring the output, and it will try to get to the actual goal. It also makes it insensitive to internal changes in the system. So if you haven't got a very good model of the system, it doesn't really matter quite as much, because what you care about is what it's doing, and you're not necessarily assuming that you know exactly how it's working. Another thing about using feedback is you can actually make something which was unstable into a stable system. And a good example of this would be, the inverted pendulum. You can have a pendulum balancing which is inherently unstable, but because you've got a controller which is looking at the angle to the vertical and trying to keep it to 0, you can actually make a system which was inherently unstable into a stable system by using feedback. There are, of course, disadvantages of using feedback, or should I say there are issues. And one of the real main issues is the fact that you can end up with an unstable system. So it leads to instability if you don't use the right amount of feedback. If you end up using something that generates positive feedback, the system will go unstable and maybe try to theoretically go to infinity. And of course it makes it a bit more complicated, but that's not really a big issue. So let's think about signal flow graphs for feed forward and feedback control. We'll start off with feed forward control, and here is typically what a feed forward system will do. You have, or what it's built of as well. So we have a goal, so it could be that it's a position that you want to get to with a robot. We're going to drive through an inverse model, so it's going to map what we want into what we need to tell the plant or the system in order for it to do what we want it to do. So we showed this previously, that this is then a good way of generating the appropriate motor command. But the idea is, this inverse model part, it could just be a rescaling, or it could be a re-representation of the data such that it does the inverse of what the plant does. And the idea is the inverse model in series with the plant means that the output should be as much as possible equal to the goal after we've finished. Now, like I said, we're not looking at the output there, so we just hope that it's working, and if the inverse model is a good model of the plant, then it should do quite well. However, if we don't know the model of the plant, then we've got a problem, and it doesn't deal with disturbances, as we said before. That's when we can start taking advantage of using feedback from the output. So this is now the model of an output feedback controller. We have the goal coming in just like we did, and there's still a feed forward path, right? We can still have a sort of inverse model which kind of gets the signal into the right kind of format, or it could just be a scaling, or it could be a PID controller, or something that we want to do to help it actually control the plant. We pass that information, we pass that signal to the plant, it then generates the output. And if this controller and the plant and everything is well calibrated, it should sort of kind of move in the right direction to what we want it to do. But often that's not the case. So what we have to do is look at the actual output. We might be able to use a sensor. We're looking at the output, and then we feed back what we've actually got from the output of the system and compare it with what we wanted. And if it's not the same, we generate an error, and this error then drives the system to try to move the output towards the goal. And this means we don't really need to know what the plant is as accurately, and we don't really need to worry so much about disturbances, because if it affects the output and it doesn't quite get to where we want, the error will basically deal with that and try to force the plant to move to get to where we want it to get to. So let's now think about state feedback control equations. We know that for a state space model, we have the two matrix equations, x dot equals ax plus bu. So don't forget, x is the state, x dot is the state derivative, and u is the control input, and y is the output of the system. So now what we're going to say is we're going to use state feedback control, in which case we set u, the input, to be minus k times x. So x is going to be a column vector, and k is going to be a row vector of gains for the individual states. So we substitute the u equals minus kx into the state space equations. So the first one becomes ax minus bkx, and what we do is we just factorize out the x. Y equals cx plus du. Again, we substitute in the u equals minus kx, and we end up with cx minus dkx. We factorize out the x again, and this leads to the two expressions. Well, the one expression is, I haven't put the other one on there, but x dot equals a minus bkx, and for y we have y equals c minus dkx. So those are the two state feedback control equations after we use the input being the scaled state scaled by the negative gain. So what does a signal flow graph look like for a state space model? Well, basically it looks like this. So let's just basically look through it all. What we can see is the bit in black represents a state a state space model. So if we look at, it's going to be x dot equals ax plus bu. So let's look at the x dot part here. That's the signal here. So how we get that? It's going to be ax. So if this is x dot, we need an integrator to get to x. Here's x, so we feed that through a. So first of all, this is the ax component, and we add on the u coming through here multiplied by b. So this is bu. So this is going to be ax plus bu equals x dot. We integrate x dot and we get x. The output then is going to be it's going to be cx, right? Cx here, coming in here, plus d, that's u times d, du there, and we add those up and we get y. That's the other output. Now, in the case of state feedback control, the u coming in here at the beginning actually is going to be the minus kx. So what we do is we tap off the x here, and we multiply it by minus k, and then we add it to the input here. The reference here could be 0, right? In fact, let's say it's 0, and then basically then we've just got the u equals minus kx going in here. And that's basically the drawing explained.